I guess that you can see my slides and hear me?
Yes.
Okay. Can I start already, or shall we wait 1 minute?
No, please go ahead. Yeah.
Okay. So yeah, first, thanks to the organizer for setting up this wonderful workshop, and thanks for letting me speak here. And I'll present this work with Srinivasa Arunachalam, Tom Gur, Igor Oliveira, and Arti Sundaram, where we link quantum learning algorithms and circuit layer bounds. So to start, let me describe it what are Boolean circuits. So you might know it, but let me refresh it. So this is a computational model that is described by a directed acyclic graph, where the leaves of this DAG are the inputs to your problem. So you have some input and you want to decide if it belongs to the language or not. So the leaves are the input to your problem, and the sink or the root of this DAG will be the output of if this input is in the language or not. And the inner nodes of this DAG is they're called gates, and they compute some functions on this input of for each gate. You have some input to it, and it computes some function that it is output. Okay. And Boolean circuits, they appear in different forms, so you can choose what different functions could be in these inner nodes. You can tell how many bits could be the input to each gate, how many bits could be the output of each gate, what's the depth of the circuit, and the depth here is the maximal distance between an input node and the output node, and also the size. And the size here, let's say, is the number of gates in your circuit. And once you fix these parameters, or at least asymptotically, you can describe the circuit classes. So for example, with a circuit class C, you can talk about circuits with a specific gate set, with a bounded depth, let's say constant, or let's say polynomial size. Okay. And since in this talk, one of the most important parameters is size, I usually parameterize this circuit class by putting in brackets what's the size of the circuits that are allowed in the circuit class. Okay, and then we can say that a language L can be solved by circuits of type C if there exists a family of circuits Cn, each one of them that belonging to this class, such that for every input, the output of the circuit in input X is equal to 1 if and only if X belongs to the language. Okay, so this is what I mean by a language being solved by this family of circuits. But here there is some detail that I glossed over, is how this family of circuits they appear. So and the point is here, each circuit here is for a different input size. So for an input size, let's say n, we have a specific circuit that computes the output of the function for all inputs of that fixed input size, and then for n plus 1, you might have a different circuit that computes the output of if the input belongs to the language for a different input size. And we say that this family of circuits is uniform if there exists an algorithm A that receives an input 1 to the n and then outputs the description of Cn. Okay, so for uniform circuits, we have an algorithm that connects all of these circuits in this family. And usually we are also interested in uniform family of circuits that can be computed with some specific complexity. So for example, we could say that we want a uniform family of circuits that can be computed, let's say, in polynomial time or polynomial space, for example. And this is in contrast with this non-uniform family of circuits, where now we have an arbitrary set of circuits, one for each input size. And the point is, in this case, these families can be very, how can I say? very heterogeneous, and there might be no relation between Cn and Cn prime for n different of n prime. And it turns out that, okay, this seems to be a very subtle, like a very slight modification in definition, but it brings a lot of weird computational power to this model. And for those who have never seen it, we can we can consider, for example, the halting problem, where we want to decide if the nth Turing machine halts. And it turns out that the halting problem can be solved by non-uniform circuits, but they cannot be solved by uniform ones. And showing a non-uniform circuit that solves this problem is very simple. So you can hard code the ith circuit to be 1 if and only if the ith Turing machine halts. So this circuit, by definition, works correctly. And on the other hand, we know that the halting problem is undecidable. So there are no uniform family of circuits that can solve it. Okay. And one of the biggest open problems in circuit complexity is trying to understand, to compare the computational power of these two types of families of circuits. And in particular, for example, we believe that okay, non-uniformity, it adds some weird power, but it should not, I think most people, or a lot of people believe that it does not add too much power. So for example, we believe that for NP, for example, it does not have, so there is a problem in NP that does not have polynomial size non-uniform family of circuits, okay? So, but on the other hand, from what we know today, it could be possible that nx, so the exponential version of NP, that it still consists with our knowledge that it could have polynomial size non-uniform family of circuits. Okay, so there is a huge gap between what to expect and what we can actually prove nowadays. And just to show as an example of how hard is this problem, so in 2016, Ryan Williams, he proved that NX is not in ACC, where ACC are circuits with constant depth using AND or NOT and mod M gates and polynomial size. And although this family, the circuit class is very small and very shallow, showing that non-exponential time is not contained in this circuit was a breakthrough and a very important result in complexity theory. And just to establish, like at least informally, our result, what we show is that if we can achieve non-trivial quantum learning for some circuit classes, then this implies circuit lower bounds. So this is a surprising way that how quantum algorithms, and more specifically how quantum learning algorithms, can help us solve a very important problem in complexity theory. And in order to, so are there any questions up to now? So yeah, if no, I'll continue, but feel free to stop me whenever there's something that's not clear. So to continue, let me first describe what our quantum learning model is. So in this learning model, we fixed a family of functions C, and I'm using the same calligraphic letter, like the same letter, because in this result or in this talk, the functions that we want, they come from circuits. And we fix a specific function f that can be solved, say there's a truth table, like this function, this is a function that can be computed by this family of circuits. And what we're interested in is in learning algorithms for the circuit class. So the idea is that this learning algorithm has oracle access to this unknown function. So here we use the standard quantum query model, where on input x and b, this oracle outputs x and b XOR f of x. And we want that our learning algorithm outputs some quantum hypothesis u that such that with high probability, U is close to F. So what do I mean by this unitary U being close to F? So what we want is that when you run this unitary on input X and some auxiliary bits initialized by 0, then the output of this unitary, when you consider the output of this unitary, it should be f of x with high probability. Okay, so yeah, this should be 1 minus epsilon here. Sorry about that. So the idea is that when you run this unitary on input x, the first qubit should be f of x with high probability. And what we want is that this happens with high probability. So the probability over this learning algorithm, we want that it outputs U that has this property with probability at least 1 minus delta. Okay, and notice that this in this model that I described to you, there are two main changes, two main differences from standard learning algorithms. The first one is that we deal with like we're allowing queries instead of samples. So usual learning algorithms, they're given samples, and here it's a bit stronger. So we allow query access to this function. And more interestingly, it also allows quantum hypothesis. So usual learning algorithms, the hypothesis is a classical circuit, but now we allow it to be a quantum unitary. But
I have a quick question.
Yes.
So sorry, I find it a little confusing. So I thought, so is there a sense in which this is a uniform model of computing, so that you know what you were saying on the last slide applies, that you're showing that comparing a uniform and a non-uniform class or something?
No, okay, about this learning algorithm, okay, let's say that this learning algorithm is uniform. So there is an algorithm that computes, like the point is the circuit class C, it could be any class, like it could be more general, it could be just a class of functions. And this algorithm A is, let's say it's uniform. Okay, so I'm just describing what the learning algorithm for now. It's not about like uniform versus non-uniform comes when we're discussing this circuit class C. Is it clear, Umesh?
No. So I was a little unclear about, you know, you said about NX versus ACC, you know, that was comparing a uniform to non-uniform class, right?
Oh, yeah, sure.
Yeah, so here, once you talk about learning, it wasn't clear to me how what the analogy is.
Oh, no, okay. So, okay. The learning, the analogy will come when I instantiate these blocks, like when I explain our result in more details. And for now, I'm just giving you some information that allow me to give precisely what you mean by this. Okay, so I'm just here describing what a learning model is, and then I think in 1 or 2 slides I'll describe our main result, and then if there are any questions there, I can stop again.
Actually, can I ask one more question? So
yes.
When the output is this quantum hypothesis U, what form is U?
Let's say you describe the unitary. I give you the description of U.
As a matrix?
As no, polynomial size circuit.
As a circuit, okay.
Yeah, let's say it's a circuit. Any other question? So yeah, I'd like just to highlight that allowing these stronger models where we allow a unitary as an output and where you have query access, it's actually better for us because our result means that if you find the learning algorithm, then you have circular bounds. So the easier it is, so the stronger that your model is, it's better because it should be easier to find a learning algorithm in this case. Okay, so this I just want to point out that these are actually helping us in some sense to find circular bounds, hopefully. So now I can describe our result in a bit more details. So what it shows is that if there exists some parameter gamma that you can pick whatever you want, such that the size of polynomial size circuits of some circuit class C can be learned with error epsilon and time t, where epsilon is the error that this algorithm, like this learning algorithm, could do is half minus gamma. And the time that this quantum algorithm can run is gamma squared times 2 to the n over n. Okay, so if you have such a quantum algorithm with these parameters, then we have the BQE. So then the problems that can be solved in quantum exponential time is not included in the circuit class C. Okay, so here, okay, what we're showing here is that if this type of learning algorithms exist, then you have this uniform versus non-uniform lower bound here. So we're showing that this non-uniform circuit class does not have this we show this lower bound to it, this uniform lower bound to it. Okay, so this is the analogous between the NX and ACC. For example, if you show a quantum learning algorithm to ACC, then we would show that BQE is not in ACC. Okay, this is the precise type of statements that we're looking for. So Umesh, does it clear things a bit?
Yeah, not. I guess what's unclear to me is to what extent there's something non-uniform already in the definition of learning. So in the ACC versus NX, there was a completely uniform class and a completely non-uniform class, and there's both complexity classes that are being compared. It's intermediated through this notion of learning, which already seems like a non-uniform notion.
No. Learning, the learning algorithm is uniform. So so the only thing that's non-uniform is the circuit class C.
Okay.
Okay.
So maybe can you say that? That's what I was asking during the definition of learning.
Sorry. So let me go back. So here we have this uniform family of circuits or learn algorithms A.
Yeah.
And it's given Arco access to this, let's say, non-uniform circuit class C. And what we want is that this algorithm that's uniform, making queries to F, output a hypothesis that approximates F well. Okay.
Yeah, good. I'll think about it offline. But great. Yeah, thanks.
Okay. So yeah, I'd like to first talk about two types of learners that we call trivial learners. And the first one is a very simple one. So you have a learning algorithm that can run in exponential time and has error 0.
Sorry, Alex, can I ask you one more question?
Of course.
Can you just say some intuition here? Okay, so naively, you say if something can be learned, then it must be very hard. So can you just point me in the right direction? It seems to be turned around for me. So why is that intuitively the right direction?
What you mean in the right direction? Why such statements are not trivial in some sense?
No. Not by it's not trivial, but so normally I would think if some class can be learned, then it's easy enough to be learned. Whereas it's saying, well, if it's learnable, then it must be very hard. So can you say some intuition about why that's
No. This is showing that this is showing that the class is hard, right? Sorry, the class is easy because it does not contain the QE.
Oh, it doesn't contain. Oh, sorry. That's why I was tender. Okay, sure.
Okay, so this is showing that this class is not so big as
Okay.
Should be true for simple classes, but this is showing that this is proving that's not true.
Okay, sorry.
Alex, there's a question from Ronald in the Q&A. He asks, if gamma is constant, then why is it written as gamma squared 2 to the n divided by n?
Oh, no, gamma could be any parameter that you want. And I'll give two examples, and in the second example, gamma will be exponentially small. So the first one, okay, the first type of trivial learners that I'm defining is that the learner that just learns F by creating all possible inputs, store a truth table, and then whenever you have some input X, it can just look to this truth table and output the correct value, right? This is a valid learner, and it runs in time 2 to the n, and it has error 0. And a second type of trivial learner that works, and they are trivial because they work actually for every possible function. So every function can be learned with time 2 to the n and error 0 by just this straightforward brute force search, like lookup table. And the second trivial learner that works for any function is by doing Fourier sampling, and it takes polytime, and it has error 1/2 minus 2 to the minus n over 2. And this learner is just by applying a Hadamard, it's just by sampling one of the Fourier coefficients of f. And it's not hard to see that this gives this approximation, like half minus big omega of n 2 to the minus n over 2. Okay, so I don't want to explain how it goes, but like it's a simple analysis that shows that this Fourier sampling gives us these bounds. And if you look to this, if you compare these two trivial learners with the parameters that we have, it turns out that a slight improvement of any of these trivial learners gives us circular bounds. Okay, because here you can, okay, the time here would, in the first learner would be 2 to the n over n, but here in this first learner we have 2 to the n. And in the second one, the error would be, sorry. And whereas in the second case, we would have time that would be, I guess, at 1 over n, but if you can bootstrap to poly n, then you already also have the circular bounds. So just to summarize, what our result is saying that if you can have a non-trivial learner, so if you can improve a little bit on either of these trivial learners, then it already implies circular bounds. And there's just some footnotes where like the circuit class, it has to be like, in order to our theorem to hold, we need the C to be closed under restriction and simulatable by poly-side circuits. But these are very standard assumptions that holds for most circuit classes that we know. And if there are no further questions, I'll try to give an idea of how to prove such a result. Oh, just before that, a way of interpreting our result is that, okay, on the one hand, we can be happy and think that now we have a new approach, a quantum approach, to prove these long-standing open circular bounds. But on the other hand, it also shows that proving quantum learning algorithms is hard, because if you're able to do that, we're also solving very important open problems.
Alex, there's another question in Q&A by Abhinav regarding the first trivial learner. Why is it a learning algorithm in the sense that you describe? How can you ensure that there's a uniform algorithm that outputs the truth table?
So you have a learner, right? Your learning algorithm is just iterate over all possible inputs and collect of the outputs, and with these you can compile a unitary, an exponentially large unitary that computes the function. So this is a valid learning algorithm by what I define here, right? So A is just iterating over all x's, collecting the output, collecting f of x, and outputting this gigantic unitary that computes your function.
There's another question from the Q&A. Ronald asks, regarding the second trivial learner, Fourier sampling returns an S such that chi sub s or minus chi sub s has error at most 1/2 minus omega 2 to the minus n over 2. but how do you know which one?
Oh,
so,
so
yeah.
that's why, oh, sorry. Yeah, I forgot to talk. So say here, delta, we want the delta in this learning algorithm to be a constant. So you can just pick one of them uniform at random, and then you have your half here. Like we're not aiming for something that is very close to one. We just need a constant here. So picking either of them is fine. Like picking one of them uniform at random will give us the right, you do the correct choice with what you have. So let me now give a summary of how you achieve a result. So the first thing is showing that a quantum learning algorithm implies what we call a quantum natural property. And this is saying that if you can learn C, then this learning algorithm can be used to distinguish the truth table of a function that can be computed by the circuit class from random functions. Okay, and I'll talk more about it in the next slide. And then the second step is that if you assume that P space is hard, then you can construct a PRG that fools uniform quantum circuits. And again, I'll define things more precisely in the next few slides. And to show this result, we use we build up on different results from the classical literature, but we need to quantize them. And for some of these results, specifically for AJKW, this is highly non-trivial. And finally, when you have these two steps, so when you have these natural properties and you have these PRGs, we can use a win-win argument. And we can show that if P space is easy, then you can find simple circular bounds. And if P space is hard, then you can use our assumption, like you can use step 2 and build our PRG that can fool this quantum natural property coming from our quantum learning algorithm. Okay, so this is the big picture, and I will try to, in the rest of this talk, try to explain a bit what we're doing in each step. So first, let me talk about natural properties. So classical natural properties, they're introduced by R&R in '97, and with the hope of at least finding a barrier to the P, of how to prove P versus NP. And what they show is that, or what they define that a property gamma is called denatural against some circuit class C if it has 3 properties. So first is constructivity. So the idea is that if you're given the exponential size truth table of some function, deciding if it is if it has this property or not, if it belongs to this, you can think about a property as a set of functions. So the constructivity asks if given the truth table of the function, deciding if it has property or if it belongs to this set is decidable in this complex class D. We also ask largeness, and the point is largeness is saying that if you pick a random function, it has this property with high probability. And finally, we have usefulness. Is the point is for large enough n, all these functions that can be computed by the circuit class with size n, does like all of these functions do not have the property. So in some sense, this natural property is separating random functions from functions that can be computed by a circuit class for big enough input size. And they use this to show that, okay, if you have hope to prove P is equal or P is different of NP, this proof has to be non-relativizing. So the idea is that this it can be not casted as this type of arguments. And our first contribution is defining for the first time what they call a quantum natural property, and it is an extension of these classical ones, where now for constructivity we want that given the truth table of the function, you run a quantum polynomial time algorithm, and the polynomial here is compared to the size of the size of the truth table of the function, so it's exponential in the input size. And we want that for large enough n, if you pick there exists a dense set gamma n, so let's say a constant fraction of the functions on n bits. It turns out that this algorithm output 1 for every input in this dense set with probability exponential close to 1. So again, here is just saying that if you pick, okay, morally saying that if you pick a random function of size n, it means that this quantum algorithm should output 1 with very high probability. And finally, we also have usefulness, where we want that for functions that are in this circuit class, they get rejected by this quantum circuit. Okay, at least except with a negligible probability. So these quantum natural properties, they are just the extension of classical ones, but then you have to be more subtle, because completeness and soundness might not be one. So these where these issues appear, or these technicalities appear, but the intuition is the same here. And our first result is showing that if you have a learning algorithm for the secret class C, then we have, with the parameters that I said before, then you actually have a quantum natural property against C. So in other words, if you can learn C, you can distinguish functions computed by C and random functions. And the idea here is just using this learning algorithm, you can compute a hypothesis to the function. And then you can just check if your hypothesis is correct. So you can just pick some inputs uniformly at random. And since notice that remember that this natural property, it has the truth table of a function, so you can just compare the output of your learning algorithm, the output of your hypothesis, with the truth table that this learning algorithm got. Okay, and we can show that these three properties of quantum natural properties hold. So by the definition, by the parameters that we choose, we have that the runtime is polynomial in the size of truth table, and also by the parameters of your learning algorithm, it turns out that random functions should not have unitaries of this size. So the learning algorithm will not be able to compute the matrix, or even the circuit, instead of the matrix, the circuit that computes these random functions. So largeness also holds. And finally, we also have usefulness by the definition, by the assumption of our learning algorithm. So we have the assumption that our learning algorithm learns well functions that are in the circuit class. So the hypothesis that is output by this learning algorithm should do well on these test inputs. Okay, so yeah, this is not very hard, but if there's any question, please let me know. Okay, the second building block are PRGs. And you might know from cryptography, these are functions that allow us to stretch some true and small seeds to a larger pseudo-random string that can fool some sort of adversaries. So let me describe it more formally, the PRGs that we consider here. And these are functions, Gn, that receives as input some n to the alpha bit string, and in output some 2 to the n to the lambda bit strings. And here you can think of lambda. Lambda is just a constant between 0 and 1/5, and alpha is an arbitrary number here, an arbitrary integer. And we have two properties that we require from this PRG is that it can be computed in time 2 to the n to the alpha, and we also require that for every uniform family of quantum circuits, CM, the output of this quantum circuit on truly random inputs, or on the output of this quantum circuit when it's given as an output of this PRG should be roughly the same. So the point is all of these quantum circuits cannot distinguish which is the case, if it was given a random input or a pseudo-random one. Okay, this is a somewhat standard definition of PRG, but here what's important are these parameters that I was trying to not get too technical, but so using this PRG, here's what we were able to show is that for every circuit class, at least one of these two things is true. So we can show that there exists a language in BQE that cannot be computed by Boolean series of size n to the k. Or we can show that given a quantum natural property against this circuit of size, like the circuit class with size n to the a, then the size of the problems that can be solved in deterministic exponential size are not in the circuit class with size parameter n to the a over eta. And so the idea of this result is by like we showed this by a win-win argument. So the first case, let's assume that P space is a BQ time 2 to the n to the gamma. Then by their result, we can show that there exists some language in P space that is included in BQE. Okay, this is directly from Oliveira Santana. And the most important, the most interesting part is showing that if P space is not in BQ time 2 to the n to the gamma, what we can show is that then we can instantiate the PRG that I described in the last slide. And this PRG, since it's secure against uniform quantum computations, it will be able to fool, like we can find, since this PRG fools every uniform quantum computation, we can use this quantum natural property to find some function that is not in the circuit class. So let me explain it with a picture. So we have that if you consider a set of all possible functions, we have the preimage of one, considering of these quantum natural properties, and we know that this set is large by the largeness of the largeness property of quantum natural properties. And we have the zero preimage. It might be small, but we also have the zero preimage. But in particular, it contains the circuit class C by the usefulness of this quantum natural property. And what we show that P space is not easy. So if P space is not included in BQ time with those parameters, then the point is this we can implement the PRG that cannot be distinguished from a random function. So in particular, this for different values of x's, this PRG should give us a truth table that lies in the preimage of one. So in particular, whenever you have some x that gives us a function that lies in a preimage of one, by the definition of quantum natural properties, it means that this function that lies here cannot have a circuit of small size. So just saying again what I explained before. So what we show that with a PRG and this quantum natural property, we can show that E is not contained in the circuit class. And I think I'm a bit running out of time. So yeah, the point is, as I said, we can see G of like fixed an input X. We can see Gn of X as a truth table of a function. And since we know that G is a PRG, so any algorithm, also the natural property B should behave the same if it's given a pseudo-random truth table or a random truth table. And therefore, there exists some input x star such that this function gn x star is not in circuit class because roughly half of this pseudo-random truth tables should fall in the preimage of 1. And the main question is, how can you find such a preimage? And the point is, we don't need to. We just need to define the right language, and the language that will be the hard one that cannot be solved by the circuit class is just by the pair x and y, where we consider gx of y. It's like the ith bit of gx. And by the conditions that we added to this to the circuit class, it means that since there exists this x star such that this function is hard, then this language is also be hard. So this lifting from the hardness of this function gn x star will be lifted to like the hardness of this language will be lifted to the hardness of LG. And we have that LG can be solved in exponential time because the time we have a time bound on the PRG size, or the PRG runtime. And we have by definition that LG is not in the circuit class because we have these hard functions. One of these for one of these x star, it is not in the circuit class. So the only remaining part of this result is showing this conditional PRG. So showing that if P space is not contained in DQ time 2 to the n to the gamma, then such a PRG exists. And this is shown by a series of steps. So the first one is using these nice P space hard problems. And then considering like the concatenation or the parallel repetition of each of these of this function multiple times, applying Goldreich-Levin trick, and finally use this function in the Nizam-Wigner construction to construct PRGs. And if you compose all the steps, what we show is if there exists a distinguisher with some advantage for this PRG, then we can actually construct some algorithm that can compute this function DL with probability at least half plus gamma. And then from a result by Adcock and Cleve, we can show that if you can compute the Goldreich-Levin of some function, you can also compute some function with some probability, with probability gamma cubed over 2. And this was the hardest technical part of our result, is showing that if you can compute some function, like the parallel repetition of the function or the direct sum of the function, with a very small probability. So you should imagine here gamma to be, let's say, 2 to the minus n over 2. Then you can come up with a circuit C that computes the function and the original function f, or with probability 1 minus 1 over pon. So from here, we're going from success probability exponentially small to almost 1. And from that, you can go using the niceness of this P-space hard problem. We can have an algorithm for quantum algorithm for P-space, but here by your assumption that P-space is not in BQ time 2 to the n to the gamma, this is a contradiction. So such a PRG, such a distinguisher cannot exist, and therefore the PRG is secure. And I'd like just to finish with some open problems. So the first one is, can you design learning algorithms and find new circular bounds? And some candidates are ACC and torus polynomials, for example. In our result, we show some efficient PRG against uniform families of quantum circuits. And one of the key points of showing this PRG is showing hardness amplification, and one I think very interesting open question is trying to find other applications of this hardness amplification in the quantum setting. And thank you for attention.
Okay, so thank you, Alex, very much. And so there were some questions during your talk. You still have just 1 minute or a couple of minutes for questions, if there is any.
What's a torus polynomial?
Good question. Yeah, I just I don't know if Igor is around or Igor knows it. Yeah, so apparently, okay, this somehow is something intermediate between ACC and C1. So something intermediate between these two circuit classes.
Oh, cool.
Okay, another question. Okay, so this doesn't seem to be the case. So we will stop now and continue in half an hour at 11:45. So thank you, Alex, for your talk.